Henny, thank you very much for the invitation, and Marty for the invitation to come out here and give this lecture tonight. If you would permit me one personal indulgence, I'd like to dedicate this talk to my mother-in-law, who unfortunately left us 2 years ago, but I'm pretty sure she's with us tonight. She was an unending source of inspiration and support for me throughout my career. Tonight I'd like to share with you some of the results of the work we're doing at the Jet Propulsion Laboratory, but as part of NASA. But you will see that I've included some other material from other parts of NASA as well. All the images you will see here tonight are courtesy of NASA and of JPL and Caltech, the university that I'm associated with. So, for thousands of years, people have been looking up at the night sky and wondered whether we are alone. Here you see a beautiful video from the Hubble Space Telescope through the Westerland star cluster area. And it is believed that stars are forming in these clouds of dust, particularly in these areas that appear like pillars that you can see in the dust clouds there. And in the background, you see the actual star cluster that was formed when this cloud of dust was actually in that position before the stars actually used up the dust around them to actually ignite. Now, if we go beyond the stars and we look at how planets form, it is believed that planets form out of the debris disk of material that is left over once a star is formed. And this particular animation, you can see the star in the middle in the cloud, which is the debris disk rotating around the star. And pieces of that disk coalesce, bump into each other, stick to each other, eventually growing bigger and bigger, and finally planets are formed. Now, if you have a solar system that is in thermal equilibrium, meaning the temperature is stable, then there is a well-defined distance away from the star where the temperature is such that water can exist in liquid form. Now, why is that important? We know that there are three things that are needed for life as we know it to exist. The first is water in liquid form. The second is the conditions must be favorable to the formation of large complex molecules. And the third one is that there has to be some kind of a source of energy to sustain metabolism. So if you look at our solar system depicted here, there is a zone that is shown in the turquoise color that you can see up there that is stretches from just inside the orbit of Venus to just outside the orbit of Mars. That is known as the habitable zone, or sometimes called the Goldilocks zone. That is the area in our solar system where we believe that liquid water can exist because of the temperature. And until very recently, the theory was that's the area that you should look in if you're looking for places where there could potentially be life. So in our case, Venus is on the inner edge, actually nowadays slightly outside of our habitable zone, closer to the sun. And if you look in the left-hand side on the screen, you see what Venus looks like if you look at it through a telescope. It's basically just a white yellowish ball. It has a very, very thick atmosphere. The temperature on the surface is far too hot for liquid water to exist. In fact, it's hot enough to melt lead on the surface of Venus. But fortunately, we have other ways that we can study the surface of planets like Venus with, and that is called a synthetic aperture radar. On the right-hand side, you see a picture taken of the surface of Venus by the Magellan mission that we flew in the early 1990s, and you see a beautiful impact crater with the ejecta from the impact crater around it. But as I said, the surface is far too hot for liquid water to exist, so the chances of us finding life on the surface of Venus are rather remote. Now, I'm going to skip over the Earth because we know there's life here. We can spend the whole evening arguing about the intelligence of the life, but there's life here. So let's look at the other edge of the habitable zone at Mars. A beautiful picture of Mars, as you can see here. If you compare the Earth and Mars, as you can see here side by side, the relative sizes, Mars is just about half the diameter of the Earth. But the surface of Mars is about the same as all the land masses on Earth put together. The gravitational pull on Mars is only 1/3 of that of the Earth. So if you want to lose weight, that's a good place to go. It has a very, very thin atmosphere, only about 1%, less than 1% that of the Earth. And the atmosphere is 95% carbon dioxide, only less than 0.8% oxygen. We would not be able to breathe and live on Mars as it is today. Nevertheless, Mars and Earth share several features. In this particular case, you can see it on the northern poles. Both of the poles are covered by ice, the polar caps. Both of them have large canyons on them. On the right-hand side on your screen is the Grand Canyon in the United States, about 400 kilometers long, about 30 kilometers wide, 20 to 30 kilometers wide, and about 1.6 kilometers deep. On the left-hand side is Valles Marineris on Mars, a series of canyons that's about 4,000 kilometers long, about 300 kilometers wide, and 7 kilometers deep, much larger than the Grand Canyon on the Earth. Both planets have large volcanoes on them. I guess you can guess the one on the left is the Earth with all the trees on it. The highest mountain on Earth is Mount Everest, about 8,800 meters high. Olympus Mons on the right-hand side on your screen is a large volcano on Mars, 21,000 meters high. The cliffs on the side of Mount Olympus Mons are higher than Mount Everest. It covers about the size of 1/3 the size of Namibia, so it's a very large volcano. And both of them have deserts, similar geology. Now, in my class at Caltech, I often ask the students to pick which one they think is the Earth and which one is Mars. But if you look very carefully, I've cheated. In the one on the right-hand side, in the top left corner, there's a van parked up there. So that's why I can tell which one is the Earth and which one is Mars. They look very similar. And down a little while later, I'll show you some more recent pictures of the surface of Mars, and you can tell that it's very, very similar to the Earth. So, believe it or not, in 2004, we had no concrete proof yet that there was ever water on Mars. There are large canyons and things like that. People have speculated for a long time they must have been formed by water, but we had no proof that there was ever water on Mars. Except, we've had satellites around orbiting Mars since 2001. And some of those satellite pictures indicated that there was a mineral called hematite present on the surface of Mars. Now, hematite is an iron mineral. You can ask the first speaker here tonight afterwards how that works. But it's an iron mineral that forms in water, typically. So in 2004, NASA sent 2 of these little rovers to Mars. They were called Spirit and Opportunity, and you can see this relative size here compared to a standard size Californian at JPL there, being tested at JPL before we sent them to Mars. They arrived in January of 2004 and set to work to see if they could find evidence that there was ever water on Mars. If you've ever wondered what the Earth looks like from Mars, that's what it looks like. We're just a little bright dot in the sky. Now, those 2 little rovers were designed to last for 90 days, 90 Mars days. And the reason we thought they would only last for 90 days is we thought that since they were powered by solar panels, that the dust on Mars would actually collect on the solar panels, block out the sun, and we wouldn't have any energy to drive anymore. Well, it turns out, as this animation shows, a series of photographs taken by one of those rovers, every day almost, these little dust devil winds come by and blow the dust off of the panels again. And as a result, one of them, Opportunity, is actually still running 11 years after it arrived on Mars, 11 and a half years now. It recently passed the 42-kilometer mark, and those of you who are runners will know that's a marathon distance, so we ran a marathon at JPL to celebrate that. Well, here's a nice picture of the Victoria crater on Mars, taken by one of our orbiting satellites. And if you zoom in on that upper left part of the crater, you can see Opportunity out there. And you can, if you look very carefully, you can see some of its tracks as it was driving up and down and around, looking for a place to drive into the crater. Now you might ask yourself, why would you want to drive inside that crater? Well, it turns out the crater is a nice big hole that exposes the subsurface rocks to us. So if we could drive into it, we can go close up to those rocks and actually study them close up and understand what the rocks are made of on Mars. Well, they quickly found the evidence of the hematite. After all, we sent them to those specific areas because our orbital imagery showed the presence of hematite there. And sure enough, these little gray spheres that you see up there, those are hematite. Some of them, as you can see, are loose, lying around. The reason is the hematite is harder than the rock in which they are embedded, and over time the rock would weather away and leave the little spheres lying around. So they quickly found conclusive proof that, in fact, this mineral was indeed present on Mars. But they also looked for other ways to understand whether water was ever present there. And here you see a cliff called the Burns Cliffs inside a crater called Endurance. And these beautifully layered rocks clearly indicate that these rocks were laid down like sedimentary rocks on Earth. In fact, closer examination of the rocks showed that this area was episodically flooded over time, but that the water was probably too acidic for any life to be able to exist in this area. So having found the proof that we had water indeed present on Mars at some point in time, we wanted to know the next step. Were the conditions ever such that life could have existed on Mars? Were the conditions such that it could have supported life? So whereas the Spirit and Opportunity both were roving geologists, this time we sent a roving chemist. This big rover that you see here, called Curiosity, is basically a chemistry laboratory that we send to Mars. It has 10 very sophisticated instruments in it, and its job was to go answer that question. Were the conditions ever such that life could have existed there? We were not looking specifically for life. We wanted to know whether the conditions were such that life could have existed. And here you see what it looked like when it was being tested inside our testing facility at JPL. The rover is now, in this particular case, is tucked inside this thing that you see up here, which is called the back shell. And this is the heat shield that this person is touching. The heat shield, you will see in a second, protected us as we were going in through the atmosphere in Mars. So I'm going to show you a quick video of how we landed on Mars in 2012 with this particular rover. And what you will notice is we come in through the atmosphere. When we reach the top of the atmosphere at Mars, we're traveling at about 21,000 kilometers an hour. This thing weighs about 3 tons, so when you're traveling at that speed, you have a lot of energy to dissipate. Now, even though the atmosphere on Mars is very, very thin, it still breaks this capsule, and in the process, this heat shield heats up to about 2,500 degrees Celsius. So that's quite a strong amount of heat that we have to protect the rover against. Now, because the atmosphere is so thin, it cannot slow us down all the way. It only slows us down to about 1,600 kilometers an hour. At that point, we open a very special supersonic parachute. And that parachute then slows us down to about roughly 300 kilometers an hour. And then we will pop off this heat shield, and you will see the rover popping out of this back shell, and then basically it will fly itself down to the surface, where it will then be lowered down on cables. And once we have the confirmation that the wheels are on the surface, we will cut the cables and fly away. Now, all of this happens when the light travel time from Mars is 14 minutes to the Earth, 14 minutes, and it takes us only 7 minutes to get down to the surface. So by the time we get the signal that we entered the atmosphere on Mars, the vehicle is already on the ground for 7 minutes. There's absolutely nothing we can do about anything we can see that's happening. We can only watch and hope that the computers did everything the way that they were supposed to. So here we go. This is how it played out on the evening of the 5th of August, 2012 for us. Here we're entering the atmosphere, as you can see. Pretty soon you will see the heat shield start heating up, as I said, about 2,500 degrees. And now we're traveling at about 1,600 kilometers an hour. We open up the big parachute. That parachute slows us down to about 300 kilometers an hour. Now we pop off the heat shield and out flies the rover with its own rockets now. And it's flying down to the surface, hovering above the surface and lowering that 1-ton rover to the surface. And you can see how nervous the people are. And when we were finally on the ground, we cut the cables and that stage just flew away. And we were safely on Mars. And that's what it looked like where we actually landed. You can see in the foreground here the shadows of the mast and the arm of the rover. In the background is Mount Sharp. We landed in a place called Gale Crater. The main reason we landed here is it showed the presence of sulfites and so on in the rocks, which we believe were indications of past water, and there are clay minerals and so on in this area. If you look in the upper right-hand corner here, those gray spots that you see there are the holes that were blasted into the surface by the rockets as we were coming down to land the rover on the surface. We quickly found evidence that this area had water in the past. This is a type of rock known as a conglomerate here on Earth. It basically is where water cements larger and smaller rocks together into this kind of a matrix, as you can see here, of materials. And we now believe that we landed basically in an ancient streambed on Mars at the end of a river system. Originally, our plan was to drive to the mountain, but when you have a whole team of scientists, everybody's interested in their own rock. Well, so first they noticed this area from orbit, and looked like a very interesting area with clay minerals and so on, to go study that. So here is where we landed, and the mountains that way, so we started driving this way first. You can see the little tracks of the rover as we were driving, and here is the rover itself, that little spot there. And this is what the area looks like. Pretty much like the Namib Desert. In fact, in 2004, when the first pictures came back, my wife said, "Oh my God, they landed in Namibia." So you can see why. It looks, and now you can tell why Mars is my favorite planet too. This looks very much like a dry plain with mudstone and so on here, as you can see, that you would find in desert areas on the Earth. In fact, a couple more close-up slides of some of the rocks in that general area. Now, Curiosity carries a drill with it, with which we can drill holes in the rock so we can see what the insides of the rocks are made of and not just look at the outside of them. If you see a geologist ever walking in the field, they usually carry a hammer with them. First thing they do when they pick up a rock is they knock a piece of the rock off so they can see what it looks like inside. Well, we wanted to do the same thing. So we drilled these holes, and this picture itself was the first major discovery from, I should say one of the first major discoveries from Curiosity. The fact that the surface itself is red is an oxidizing layer. It's basically, in plain English, rust. The rocks are rusted on Mars. But the fact that we drilled only about 2 centimeters into the rock and it's gray is in itself a major discovery. Theories suggested that this oxidizing layer may be as deep as a meter or so on the surface of Mars. And that would have precluded any organisms of being alive near the surface. But you can see here clearly it doesn't go nearly as deep into the surface as we had thought before. Well, we then scooped up some of that material. Curiosity has an arm in front, and that arm has this little scoop at the end of it, you can see here. With that, you can then scoop up the material and put it inside the rover. Inside, there are some specialized spectrometers and so on. Mass spectrometers are the instruments that we can analyze what these rocks are made of. And so we answered the question very early of whether Mars could ever have supported life. In Gale Crater, the geology in this area, with the fine-grained rock that you can see here, suggests that this is the end of a river system or a lake bed where water were standing for a long period of time. So fine materials actually settled on the surface and formed these fine-grained rocks. So water was here present. The estimates, depending on what theory you believe, are thousands of years. Furthermore, the water was neither very alkaline nor acidic. In fact, it was of a quality that humans would be able to drink. That combined with all the minerals that are needed to support life, carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, and so on, are present in these rocks. So clearly this area could have sustained life in the past. We have no evidence that life ever existed in this area, but the conditions clearly were such that when these rocks were formed, that life could have existed if it was present on Mars. Now, since then, we've been driving towards Mount Sharp. You can see here a beautiful tracks of the rover as it was crossing a little dune on its way to the mountain. And as we're getting closer to the mountain, obviously it gets a little rougher driving. You can see more slopes and so on that we have to negotiate. But still, we find lots and lots of layered rocks indicating the presence of water in the past. Now, on our way there, we had recently, Mars went behind the sun from us, so we couldn't communicate with the rover. So we parked it a little bit for a while. There it is, right up there. We parked it for a couple of weeks and just told it to sit there and wait till we talk with it again when Mars comes out on the other side of the sun, which it recently did, so we are now communicating with the rover again. On the way to the mountain, however, we encountered some very interesting terrain. Now, as I mentioned, this rover weighs about 1 ton on Earth. On Mars, of course, it's a little bit lighter, but nevertheless, it's a very heavy vehicle. Most of the time when we drive across rocks, over rocks and stuff like that, let's fix this up a little bit, the wheels just press the rocks into the surface and there's no problem for us. But for a while we drove over a very hard area where the rocks were not, we were not pressing the rocks into the surface. In fact, the rocks pressed holes in our tires, as you can see up there. And here's another picture of a much larger hole in one of our tires, as you can see there. These tires are aluminum tires, so they can take a little bit of beating, but when the nearest tire shop is a couple of 100 million kilometers away, you have to take care of the tires. Now, since then, we have figured out how this happened and what kind of terrain causes this to happen, so we are now avoiding that kind of terrain, and we should be okay with the wheels for quite a while to come. We had other interesting discoveries on Mars. Here is a measurement of the gas methane on the surface of Mars. On Earth, methane is often associated with biological behavior, but it can also be generated non-biologically. And as you can see here on the bottom is a scale that goes by 100, 200. Those are days on Mars, sols we call them on Mars. And you can see there for a period of about 60 sols or so, the level of methane where Curiosity is increased dramatically, about a factor of 10, and then mysteriously decreased again. We do not know what caused this, and of course this is one of those interesting finds. Often when you do research, you find one thing and it opens 10 other questions. This is one of those. But we'll be continuing to measure methane and see if we can see evidence that this is happening again. People have indeed made similar measurements in the past with telescopes from the Earth that suggested that maybe there are these short events of increased methane sometimes on Mars. Another discovery is the organic molecule chlorobenzene on the surface of Mars, but you can see here it's not in all the rocks that we've looked at. Here are 4 different sites that we looked at, and in the Cumberland area, indicated by the green bars, we saw a significant increase in the amount of chlorobenzene, and the other ones basically are, the levels are right at the detection limit of our instruments. But to prove to you that it indeed is chlorobenzene, the inset at the top there is a comparison with a laboratory sample on the Earth, the measurement of the spectrum, and you can see they fit very, very well. So indeed, this molecule is present on the surface of Mars. So, but the rovers only tell part of the story on Mars. If you give me this second, let me fix this up before it falls off here. There we go. This shows a series of images from one of our orbiters, and it shows these streaks that are forming on the side of a cliff on Mars. In the beginning of the summer, the ice near the surface actually melts, and it forms these little seeps that we think are very briny water on the surface of Mars during the summer. Now, we will not be able to drive to these places with our rovers. They are on very steep slopes. So we will have to find other means to get to these places, but the point is that there is water present on the surface of Mars even today. Now, how are we going to get there? Well, we're working on these kinds of little things. This is a little helicopter that we're planning to take potentially to Mars. NASA just gave us some money to prove this concept, and potentially we can take it to Mars in 2020 with our next rover. Now, in 2020 case, we will just use this little helicopter to scout ahead of the rover to help us with the driving. But eventually we would be able to take these little things and put real scientific instruments on them, and then fly up to potentially to places like that. Now, keep in mind, on Mars, you cannot fly this thing with a joystick from the Earth. The signal takes 14 minutes to get there. So this little helicopter will have to take off, fly, and land all by itself with its own computer. Moreover, there are no GPS receivers on Mars or GPS satellites, so there's nothing to tell it where it is. You have to actually recognize the terrain that you took off from the pictures you took when you took off. So we're working on those kinds of things at the moment and testing this little, here you can see it flying, just taking off inside our chamber that we pumped down to 1% atmosphere of the Earth, so we can show that it can actually fly on Mars. There are also, if there is water near the surface of Mars, we know on Earth that typically in caves you find moist environments, and potentially that's areas where, those are areas where bacteria and so on might actually survive. Here you see the entrance to two caves on the surface of Mars. These are, we believe, collapsed lava tubes on the surface of Mars. But if you zoom in a little bit, you can clearly see these are holes in the ground where potentially these kinds of bacteria and so on might have survived if they are there. But again, we won't be able to drive in there with our rovers, and we won't be able to fly in there with our little helicopter. So we are actually working on technologies like this little Gecko rover that you see here that can climb up on a rocky surface like that, and in a little while you'll see it'll can actually climb upside down, cling to a surface of rocks, and so there you go, climbing around along the surface there by itself. So with these, we hope to be able to explore underground caves and things like that, not only on Mars, but on other moons and planets in our solar system. So the next step to Mars is in 2020, we will take a large rover, and this time it will basically look exactly like Curiosity, except it will have instruments that can look for organic material on the surface of Mars and see if we can ever find that there was ever organic material present there. But as I said earlier, the theory suggested that we should look inside the habitable zone if you want to look for places where life could exist. But let's move outside of our habitable zone, well outside, to Jupiter, and in particular to one of its moons called Europa that you can see here in front of Jupiter. Europa is a very interesting moon. Here you see a close-up of it. You notice only one large crater on the surface of Europa, which you can see there. That suggests that this surface is very young. Well, we know the moon isn't that young. This particular moon isn't that young. So if the surface is young, then it must somehow regenerate itself and erase evidence of these kinds of impact events that happens on it. And if we look very closely at the surface, you can see it's covered in these large cracks that run almost across the entire surface here. And if we zoom even closer, that's what those cracks look like. The bluish-white background is basically pristine water ice, and the reddish areas are ice, water ice, mixed with hydrated salts. Now, where does that salt come from? The salt comes from, we believe, a subsurface ocean that is salty just like ours. We know that it is salty because it modifies the magnetic field of Jupiter in the vicinity of Europa. So we have there must be a conducting medium on the surface, which we believe is a liquid ocean underneath this ice crust. Another close-up shows these little things called lenticulae, which is basically just the Latin for freckles. These are areas, we believe, where the ice was melted from the bottom and then formed these little pits on them. These features are about 10 kilometers across, so they're fairly large areas. And here is an extreme example of that. This area here is about 70 kilometers, 80 kilometers in this direction, about 60 kilometers in that direction. And if you look very closely, you can see plates like these that broke off from there and then drifted away a little bit and then froze in place again. That happens, of course, in our polar oceans as well, when ice breaks off and then the thinner water inside the leads can freeze again during the winter time. What we believe is happening in these areas is an extreme event of large area of hot water that came up all near the top of the surface and almost melted all the way through. So what's going on this moon? Well, there are two theories of what's going on. Both of them start with a mantle that is volcanically very active. Why volcanically active? As this moon rotates around Jupiter, the tidal forces from Jupiter, as it's going closer and further away, causes heat friction inside of the moon, creating volcanism just like on our ocean floor. In the model on the left, the ice crust is relatively thin. The hot water makes its way to the top, and then it can melt those areas. And of course, the tidal forces, as it stretches this moon as it goes around Jupiter, causes those large cracks in the surface. And you can see, in some cases, the salty water from the ocean can actually escape, and that's how that's the theory of how the salt appears on the surface. And the one on the right, the ocean is not quite as deep. The ice crust is thicker, but nevertheless, the ice crust has a cold top and a warmer bottom, and these warm plumes of ice slowly migrate to the top, almost like a glacier on Earth, and then causes those deformations that we saw. In either case, if you compare Europa with the Earth, you see Europa on the left, it's slightly larger than our own moon. It's about the same size as our own moon. And then you see the Earth is much, much larger. However, the amount of water on Europa is twice as much as that on the Earth. Salty ocean, heat, and liquid water. All the ingredients that we need for life, way outside of our habitable zone. But if we go back there, we have a plan. NASA has given us some funding to study a concept known as the Europa Clipper for launch somewhere in the early 2020s to this moon. This mission will carry a series of instruments. These things that you see here are the antennas of a radar system that will be able to look through that ice and tell us how thick the ice crust is, so we can determine which one of those models is actually correct. We will also have spectrometer imagers on board that can tell us what the chemical composition of the surface of the moon is. So hopefully late in the 2020s, we will actually arrive there and we will be able to solve this mystery of what this moon is actually made of. Now, if we move further out, well, this is just a nice artist's rendition of what we might find if we actually land on the surface of Europa, which we would dearly love to do sometime in the future, but it probably will not happen on the first mission there. But as I said, if we move further out to, say, Saturn, Saturn is a very beautiful planet, as you can see here, the second largest planet in our solar system, with these beautiful rings around it. Now, Saturn has more than 60 moons. Here is a very interesting one, Hyperion. It looks basically like a sponge. It's only about half the density of water, so it would be able to float if you put it on water. But that's not what we actually went there for. We originally went there to study this moon called Titan. Titan has a very thick methane atmosphere, and some theories suggest that the primordial Earth had a similar thick methane atmosphere originally. And here you can see it, a close-up of the moon as we were flying away from it. There's the hazy atmosphere over here, and there's the rings of Saturn in the background there, and Saturn's limb actually itself. If you look at the surface of Titan, that's what it looks like. We launched a little probe with the European Space Agency called Huygens. Huygens actually landed on the surface of that moon and took this picture. A hazy place. We cannot see through that atmosphere with our regular cameras, but again, we carry a synthetic aperture radar on that mission. And here's a picture of the surface of that moon. It's the only other place in the solar system that we know of that have rivers on it today. You can see here a river system going in here, draining into this large lake over here. The only difference, of course, is these are hydrocarbons, basically like gasoline. So if you were to fill up your car, you drive up to the river and fill it up. Just don't smoke anywhere on that moon. That would not be a good idea. But this moon of Saturn, called Enceladus, proved to be a very interesting object indeed. Here you can see an image taken by the Cassini spacecraft, and it has these plumes that look like basically geysers coming out of the bottom of that moon. And a close-up shows here how whatever that liquid is spewing out of this moon high into the air, about 100 kilometers or so into the air. So we challenged our navigators, asked them to fly close to that moon so we can see what those plumes are made of. And in fact, they flew only 25 kilometers above the surface through those plumes. Not quite a feat if you think that this is more than 2 billion kilometers away from the Earth, to navigate that accurately, to be able to fly just above the surface of it. I'll keep you in suspense a little bit about what those plumes are made of. Let's take a look further at this moon a little bit more. Here you see what the moon looks like a little bit closer up. The northern half has craters on it. Looks like an old surface, something that you would expect in the solar system. This part has almost no craters in it. Again, indicating a very young, geologically speaking, a very young surface. You also see these blue cracks that we call tiger stripes. And a close-up of that is shown here. Looks very much like the cracks on Europa. Now on Cassini we have a thermal imager, which we basically can measure the temperature of the surface if you want to, and here is what that looks like. In those cracks, the temperatures are significantly higher than outside of the cracks, away from the cracks, I should say. It's out of these cracks that those plumes are emanating. That's what they're made of. It's ocean water, water vapor, methane. It has both simple and complex organic material in it. So again, a place where we have heat, we have liquid water, we have organic material, a prime place where life could exist. In fact, this is what the theory is of what Enceladus is today. It has an ocean that covers at least the southern part, and it's out of those cracks, as I mentioned, that these plumes are emanating and spewing basically ocean water into the air around Enceladus. So these are just two examples, and you've seen now two examples outside of our habitable zone that has water on it, when there's only one that we know of inside the habitable zone. Since then, people have taken another look at the other moons of both Jupiter and Saturn, and several of them are now theorized to have subsurface oceans, similar to what you see here on Enceladus and on Europa. So we may have to rethink entirely our theory of what habitable zone actually means in a solar system. So let's move outside of our solar system and look at what is out there beyond the solar system. You can see here in 1584, Giordano Bruno theorized that there are countless suns out there and countless Earths all rotating around those suns just like we do. In this case, you see exactly like the 7 planets of our own solar system. And he also correctly describes that we can only see the suns because they are large and they are luminous. We do not see the planets because they are small and they are dark. This is exactly what is the truth. There is about a factor of 1 with 10 zeros, 1 with 9 zeros, or 10 zeros in difference in brightness between the sun and a planet like the Earth. So it's very, very hard to see the Earth next to a sun like that. Now, Giordano Bruno got burned at the stake for saying stuff like this. Today, we're a little bit more lenient to people with crazy ideas than we were back then. Now, how hard is it to make an image of another planet? This is the best image we would be able to take of the Earth if we take the Hubble Space Telescope roughly to the orbit of Jupiter. This image has a resolution of about 160 kilometers. Not a nice picture, not a very sharp picture, but if you are a scientist, you say immediately, wait, but it doesn't matter. I can see there are oceans, I can see there are clouds, and I can see that there are continents on this planet. Good enough for me so far. So how hard is it to make such a picture if we were to take the Earth and we put it around another star? So let's move the Earth to the star that's closest to us, 4 light years away. You will need a telescope that's about 15,000 times the size of the Hubble Space Telescope. How big is that? Well, the mirror of the telescope will fill False Bay. It's about 30 kilometers in diameter. And the telescope itself will be more than 200 kilometers long. So it's going to be a little bit difficult to get something like this into space. Now, fortunately, there are other ways that we can find planets around other stars. We don't actually have to make a picture like that. And how does that work? Here is one example. It's called the transit method. You see the planet going around the star there, and every time when the planet comes between us and the star like this, it blocks out a little bit of the light. You can see in the curve on the left there, that shows that the light went a little bit, the star, as we're looking at it, would appear to go a little bit dimmer for a while and then comes back bright again. The bigger the planet is, the more light it will block out, and the more that the star will dim. And for planets like the Earth, it will only dim about 1 part in 20 million. So it's very, very, very small amount. But nevertheless, we built a camera called Kepler. You can see here a 100 megapixel camera. We put it in a medium-sized telescope, only about a 1.5 meter diameter mirror in it. And we launched Kepler in 2009. And Kepler looks at the same 150,000 stars all the time. And all it does was looking for those dimming events, when one of those stars appears to go dim for a little while and then come back bright again. So let me take you on a history of discovery of planets. First, we will look at our own solar system. Here you see 1785, Uranus is discovered. And then in 1801, roughly, Ceres is discovered and called a planet for a while. In 1860, just after Neptune was discovered, Ceres was demoted from being a planet to an asteroid, and we're back down to 8 planets. Pluto will appear in 1930, but alas, as you know, Pluto only joined the club for about 76 years or so, and then it was thrown out of the club as well. 1995, we will discover the first planet outside of our solar system. There it is, popping up. The blue ones we found with a technique known as radial velocity. I'll explain that in a little while. The green ones that you see on the screen there are ones that are found by this transit method, where we look at the star and it dims a little bit. Now, in 2009, we launched Kepler. You can see we knew about 400 planets about that time. The size of the planet is up here. There is Jupiter over here. Here's the Earth. That's Venus. That's Mercury. So here comes Kepler with all the green ones. Added about 1,000 planets so far. 4,000 candidate planets, of which about 1,000 of them have now been confirmed to be planets. And you can see many of them are actually smaller than the Earth. They're below the Earth on this curve. But they are also much closer to their suns. Now, that's not surprising, because many of these suns are dwarf stars. So they're much cooler and smaller than our sun. And so their habitable zones are much closer. Here's an example. Kepler 186, you may have heard of it. The names are not very imaginative. It's a 186th star that Kepler looked at. And the way the planets are named, the closest one is B, and then C, and then D, and then E, and then F. You just keep on going like that. Kepler 186F, compared to the Earth here, you can see very similar to the Earth. Well inside the habitable zone of that star. It's an M dwarf star, so it's much cooler than the Earth. The habitable zone is much closer than in our case. With 4 other planets basically inside the orbit of our Mercury, closer to its sun. Now, we found very, very strange solar systems out there. Some of them have planets as big as Jupiter going around their star in only 4 days. So imagine an entire year in 4 days, a season every day. So because they are so close to their star, of course, they're much, much hotter. So here you see the Kepler 186 system. Now, eventually we do want to make images of stars and their planets. We want to take nice pictures and look whether we can actually analyze the atmospheres of those planets to see if there's life on them. See if we can find gases like ozone and so on that we typically associate with biological activity. And one way to do that is shown here in this animation, is to take what we call a star shade, a very large inflatable or extendable sheet like this, disk, that you will then extend like this once we get on orbit, about 50 meters in diameter, and we will fly it a couple of 100,000 kilometers ahead of our telescope and block out the light of the star, as you can see there, and then we can see the planets revolving around the star. To give you an idea how hard it is to do that kind of a measurement, because the planet is so close to its star and so dim, it is the same as you're trying to take a picture roughly from Johannesburg on that, you look at that soccer stadium in Cape Town, and you look at one of those very bright lights that they use to light up the field during the night. If there's a firefly sitting on the edge of that light, you're trying to take a picture of the firefly from Johannesburg. That's what this is. That's how hard this is. So, but hopefully, in not too long from now, roughly about 10 years from now, this technology would be ready to fly, and we would be able to launch this hopefully within the next decade or so, and then we could start the era of taking pictures of planets around other stars. So I hope you enjoyed the journey with me and some of the work that we're doing at JPL. And I'm often asked the question, so are we alone? I don't know. All I hope is that somebody in my lifetime will find some evidence of some biological activity somewhere else. Thank you very much for your time.